So, is everyone hearing me loud and clear? Thank you. So, good morning. I'm Radim Krčmář. I work as a KVM developer for Red Hat. And today we'll be having a talk on self-virtualizing Linux on x86, which it worked a while ago. Sorry. Not working anymore. So, the talk will begin with what self-virtualization means. Then most of the talk will be spent by giving a description of how hardware allows us to implement it. And I said it's going to be on x86, but this presentation will only cover VMX, which is the x86 Intel implementation of hardware virtualization. And in the last part, I'll show you how a Linux implementation looks like. So, what is this self-virtualization? The basic idea is that when you normally boot Linux or an operating system, it just has direct access to all hardware it needs. And then a guest introduces a layer in between that can intercept those accesses to hardware and forbid them or modify them. And self-virtualization means that the guest and the host is basically the same entity. So it's going to be one part of Linux that controls another part of itself. In the diagram, you can see that Linux is just going to split and install itself over the real hardware. And when the host is also a guest, we have some advantages over the standard virtualization that needs them to be really isolated. So now the host can access guest's data in case you need to inject some packets or whatever, then it's already being provided. And it doesn't need full isolation, which means you can get better performance. And the sharing of devices is that also logging is already implemented for you if you wish to use it. And then you can implement it really fast. And the demonstration is just 750 lines of code. And that's including copy-pasted blocks from KVM because I wasn't sharing all of the code. And now we are maybe asking what it's good for. Well, the main reason I brought this was to show you how the VMX extensions work, so we would have better understanding of virtualization and its possible pitfalls. But we can also do it for hardware enhancement, because a guest usually doesn't have access to all the hardware that the host has. But on the other hand, we can also emulate some hardware in the in the host or hypervisor. So, for example, new Intel processor features like trapping CPU ID while in user space, or supervisor remote access prevention, which prevents the Linux kernel from accessing user mode data without it being intended, then this can be implemented even on hardware that doesn't support them, just by trapping from the guest part of our Linux into the host part or hypervisor part. Another option is if you implement proper isolation of our host and guest layers, you basically have Intel kernel guard technology, which can prevent or lock any access to hardware. And the third one, which maybe is most interesting, is that guests have some features that are not available for the host, which, for example, is TSC scaling. So if you had a host that can set up the guest in a way that triggers almost no VM exits and has no performance overhead, then you could use this feature, and any time read you do would be faster, because currently you have to scale the TSC, which means that you have to multiply it by its frequency and then add some offset. And hardware would do this for you. But the main problem of virtualization is that if you want more control, you, on the other hand, lose performance. So every time you need to implement more features, you can be sure that it's going to cost you, and the guest is going to run slower because it needs to trap into the host more often to do what you are wanting to do, and the hardware doesn't support. And in this talk, we'll focus on the minimal overhead implementation, which, if the situation was ideal, you would just set up once the split into the host and guest, and then you would run the guest, and it would basically never exit. So the host would just do the setup, and then the guest would run, and it would run as if nothing happened. So the performance wouldn't be affected. Like, this would be, of course, completely useless, but then you could just pick any single feature from the hardware extensions you want to trigger just the VM exits you are interested in, and not have any additional overhead, because the hardware features don't allow you to have all those VM exits you want, but also force you to take VM exits on things you are interested in. So now how actually the virtualization is going to be implemented in hardware is with the Intel virtualization technology, or it's usually called virtual machine extensions if you read some programming books, for example, the SDM, Software Development Manual. So a general overview of what a virtual machine is can be said to be, when you have hardware, it has some state. It's usually called registers. And if you have a virtual machine, then you want to emulate this hardware for some other operating system, for example. And then you want to switch all those hardware registers to be the virtual machine, and then you want to switch them back again. So you need at least 2 sets of these hardware registers that are going to be switched as you go back and forth between the virtual machine and your bare metal. And then there are usually virtualization controls, which just decide when the hardware is going to exit. So if you could control that the hardware never exits, then you would VM enter and never get the control back from the guest, which would basically mean that the guest registers would be in the hardware registers forever. VMCS, or Virtual Machine Control Structure, is the Intel implementation of the general idea. It has VMX controls, it has VMX information, host state and guest state. And VMX controls usually have some controls that affect when the VM exits. And then host state is a subset of host registers, and guest state is as well, but it has more registers because it needs to be more complete, as the guest doesn't know that it's running on a virtual machine, but the host does, so it doesn't need to access all those registers transparently. And VMX information is provided by the hardware to tell you when an exit happens, what the guest did, and what can you do to resume the guest back. This is, for example, the instruction length, so you don't need to implement a decoder in your hypervisor. So, and now the self-virtualization with VMX is going to be in 6 steps. You first enable those extensions, then you set up the control. It's probably my phone. Then you set up the control structure, and then the important instruction that switches from the host to the guest is VMLAUNCH. And after VMLAUNCH, you'll eventually get a VM exit, which you will handle, and then VM resume the guest back. And the exit and resume is going to continue as long as the machine is powered on. Enabling VMX is fairly straightforward. You just first should detect that you have it, and then set the VMX enabled bit in controller register 4. Then you reserve some memory area for VMX operation, and you execute VMX on. After VMX on, Intel describes the state as a VMX root state, which we are going to call also host state or hypervisor. So VMX in root operation is the one that can call all those other VMX instructions. Yep. So following enabling VMX, you can now set up VMCS. You also allocate some memory for it, and then you load it into the hardware because it has some extra registers for it as well. And then you access it with VM read and VM write. The setup has 3 main parts. You set up VMX controls, you set up host state, and you set up guest state. VMX controls are mostly controlling VM exits, so most of them are luckily going to be disabled for our self-virtualization, as we are not interested in any exits right now and want to have maximum performance. So these controls are pin-based VM execution controls, primary processors-based VM execution controls, but here are 2 features that are actually needed to eliminate more VM exits, and those are MSR bitmaps that only say that for all those MSRs, don't do any VM exits, and activate secondary controls. And in secondary controls, we can enable 3 instructions. It's invalidate PCID, read TSC with processor, and save the FPU state. And if we didn't do that, then these instructions would VM exit, and we would have to emulate them in the host. But there is no point if the hardware can do that. Then in VM exit, we just set up this bit to make sure that the host space is preserved. And in VM entry, because we are going to be entering in 64-bit mode already, then we set up this I32E mode. And the host state is very simple. You basically have hardware registers that are on the host at the point you want to self-virtualize them. And so you just copy them into the host state of your VMCS. But the VMCS doesn't have entries for all hardware registers. It just has segment registers like code segment or stack segment, controller registers, which are CR0 or flags or even RIP or SRP. And then, because on the host side for your hypervisor, you have to have some code that's going to be the new host after the split into the guest and host. And the host state is then going to fall back into your host state, into your host handler. And its stack also cannot be the same as the original stack, because that would overwrite and disturb the execution of your normal Linux operation. So you just allocate new memory and set it as a stack. And the good part about this state is that it doesn't change from now on, because the host is not going to be modified while the guest is running. The initial guest state begins the same. Because you have only one set of hardware registers at the point where you start to self-virtualize. So you just copy them all into the guest state in VMCS. It has a few more registers for you, like the SM base or DR7 or R flags. But the important part is that if you want to enable VMX in the guest, you need to hide that you have already enabled VMX in the host. And this is about the only modification we do to the guest we are going to run. And this is just done by masking the VMXE bit in CR4. The guest also has interruptibility and activity states, and it's going to change a lot. So this is just the initial state for our first run. And then as the guest or the original Linux continues its boot, it's going to update this structure. And on every VM exit, we'll read it. You could have noticed that the hardware registers that there are more hardware registers than can be put into the guest state. And these are the mainly general purpose registers, RAX, RBX through R15. And machine-specific registers which there's a lot of them, and some of them might be even undocumented. So Intel just decided that all of them are going to be preserved across VM entry and VM exit. And because when we enter, we don't want to actually modify anything, we don't have to do anything. So we just ignore that these registers exist and can VM enter. Now we have done the enabling of VMX and setup of VM control structure. So we are ready to enter the guest we have prepared. It has all the information from the hardware registers it needs to just resume operation. And VMLAUNCH is the instruction that is going to do it. VMLAUNCH just loads the state from VMCS into hardware registers. And because we have modified the instruction pointer to begin just after the VMLAUNCH instruction, the guest is going to think that VMLAUNCH maybe wasn't even executed, and is going to continue execution as if nothing happened. This will mean that it will then return to its normal boot process, finish booting, and you have your Linux that is sort of virtualized. But things are not that simple, because in VMX non-root mode, which is what is the processor state in after VMLAUNCH, compared to VMX root mode that is after VMX on and before VMLAUNCH, some instructions and operations behave differently. And one of the main differences is that you can get a VM exit. There are 64 basic exit reasons. Basically, a lot of instructions have their own, or you can get interrupted. and get a VM exit, or you can just set up some timer to expire in VMX and get a VM exit. But we have disabled almost all of them, but some VM exits can't be avoided. And this is VM call, which is an instruction whose only purpose is to force a VM exit, so it's quite understandable. But then there are CPU ID instruction, which could have been emulated in hardware, but it would probably require too much information to pass into the hardware. So designers of the VMX just decided to exit into hypervisor and let it handle it. And then there are MSR reads and writes, because there's a lot of MSRs. Not all of them fit into our MSR bitmaps that said don't care about these MSRs and just write them directly into hardware and back. Then accessing these MSRs is going to cause a VM exit. And then there are VMX on and VM pointer load, the instructions we use to actually virtualize ourselves. And hardware doesn't support or accelerate hardware virtualization, which gets us into a VM exit every time we would try to self-virtualize our self-virtualized system. So when a VM exit happens, the most important part is that the guest state is saved and into VMCS, and the host state is loaded from the VMCS. So the execution begins with the host state again. In our case, it's going to be some part of Linux that is going to handle this VM exit. But not all those registers, hardware registers, are saved. So for example, general purpose registers are still only in the hardware, and our VM exit handler, which is being called from the loaded VMX host state, must first save those registers that it's interested in and would probably want to use during its execution. So general purpose registers are pretty much used all the time. So just after a VM exit, you save them into some memory area, and you can't use any general purpose register to do that. So you only basically have the stack pointer or your instruction pointer to do that. So after all those general purpose registers are saved, you can read the exit reason, and if you know what to do, which you should in the hypervisor, you can perform an action that's based on the exit reason. So for the instructions that we have seen that cannot be whose VM exits cannot be disabled, it's VM call. You can just inject a undefined instruction intercept or do whatever you want. Maybe you want to have some action to do on the VM call. And then there are the CPU ID and MSR accesses. And because you can't do anything better than just executing them in the host and passing the results to the guest, then this is usually what is going to happen. It's just the guest is going to reach an execution of a CPU ID instruction. It's going to VM exit, and then the host will execute the CPU ID instruction instead of for the guest and load the output of the instruction into guest registers and resume. So the guest will think that it executed the instruction successfully. And the last part is VMX instructions, and sadly they cannot be simply executed in the way that CPU ID is, because that would override our self-virtualization. So we need to also implement nesting. And nesting is a weird beast. It's often confusing to talk about. So when on hardware, you run your first Linux host, then you run your Linux guest, and then you run its guest. We usually call that the host that runs directly on the hardware is L0. And the next level is L1, then L2, and so on. But usually we don't get too much higher than L2 unless you really hate performance, because we'll see what the main drawback of virtualization is, of nested virtualization is. The hardware has almost no acceleration for it, so you cannot just exit from L2 directly to L1, which you would like to. For example, if L2 in executed CPU ID, you know that it's going to be handled in L1 because L1 is the hypervisor that controls L2. But due to the lack of hardware features, L0 must never lose control of the hardware virtualization. So every VM exit that is going to happen must always go to L0. Then L0 will take a look, see that it's an exit from L2. Oh, and L1 is going to handle it. So it VM enters L1, passes the exit information it got into L1. And then when L1 finishes handling the VM exit, it cannot just directly enter back into L2, but must go through L0 again. And this overhead is going to be quite significant when you start adding more levels. So now that we want to know what we roughly want to do in nested VMX exits, we can implement them. We can't use any hardware checks like the other instruction did. So, for example, for a VMX on, we'll just perform all the checks. That mean if the CPU ID is enabled, if VMXE in CR4 isn't set, and so on. And if the checks pass, we will just remember that L1, or the guest that's trying to be a hypervisor, entered root operation. And VMX on also provides a VMX area, so we will remember where it is. Then VM pointer load, again, we'll check everything, and just remember what VMCS is active right now in L1, but we won't execute VM pointer load, do it ourselves. And VM read and VM write are luckily emulated by hardware, so we don't have to do that, but otherwise it would be just simple memory accesses. And now to the complicated part, because VMCS or level 0 must never lose the control, then it must always be the host state in VMCS that is being executed by VMLAUNCH. So when L1 wants to VMLAUNCH itself, it traps into L0, and L0 then performs that the VMCS provided is sane, or at least its host state is sane, and then loads everything except the host state into a newly created VMCS, which can live in the VMX area provided by VMX on. And when the new VMCS is merged out of the L0 VMCS and the VMCS in L1, then the L1 can do a VM launch that's going to enter L2, how we say it. For better clarity, these VMCS are called 0 to 1, which means that it enters from L0 to L1, and VMCS 1, 2 is from level 1 to level 2, and the result is going from level 0 to level 2. And after launching the L2 from L0, then every exit is going to go back to L0, but we know that L1 is the correct one to handle it, which means that right now we just have to pass the VM exit we got back into L2. And this is also operation that combines 3 VMCS. But now we have the information we got from exit from VMCS 02, which is the VMX information, and we copy it into the VMCS 01, which is going to launch the L1. But if the L2 exited directly into L1, then it would copy its host state into hardware registers. So right now, when we are launching L1 from L0, we need to copy the host state into guest state, which is done. This host state is copied into guest state of the new VMCS we are going to launch. The information is just copied here. And then we have VMX controls and host state for the original VMCS that launches L1, and we just use them. So again, this VMCS is going to exit back to L0 and only has the host state from the VMCS 1.2. There were some instructions that we haven't used in our self-virtualization, but still need to implement if we want to self-virtualize, because Linux guest is going to use them. And these are, for example, vmclear, which just forgets that the VMCS is active and flushes any changes that might have been pending to it, and vmxoff, which disables the VMX instructions. Now we know what happens after VM launch and how first VM exit is handled, but we still don't know how to continue the execution forever. But VM resume is just basically the same as VM launch. Just we have one additional task to do, because on VM exit, the guest has some state in its general purpose registers. We have saved it, and now on VM resume, we must restore it because the hypervisor clobbered it in between. And after this is done, we are sufficiently well featured to implement self-virtualization. So now it's going to just VM resume, and then after every VM exit, for some reason that we are going to handle, we'll VM resume again, and this will continue forever. So how is this implemented for Linux? We already have most definitions of those VMX structures and other useful functions like VMX on and VMLAUNCH, thanks to KVM that is in kernel implementation. So we can just include their header files and either refactor the code or copy-paste it. And then we only have to insert our entry point of self-virtualization somewhere, which is best done during boot of the guest. And there are two considerations. You want to do it as early as possible to get maximum control, but then you also don't want to do it too early, because then you might not have some features that you would like to, or it would create more complication for the guest side, because you are allocating memory, and if you would have to say to the guest that don't touch it or just make it not available from the hypervisor, it would be harder than to letting the kernel allocate it for you, knowing that it won't use it for the second time, and then you have no problems. Another nice thing is that you can use sharing tracing mechanisms like print case for ease of debugging and development. And you can also, if you decide to, just switch back and merge them again, like strip the self-virtualization and gain performance in case you like to. But it always depends on what you want to do with this self-virtualization. From quick tests with the implementation, that because VMX doesn't allow exitless operation, we got one read MSR and about 32K VM exits, CPU ID VM exits during boot. And the overhead of a VM exit is 800 cycles on a Haswell machine. So the boot is going to be about 10 milliseconds longer than it would have been, which I guess isn't noticeable because just one daemon extra is going to take much longer. And if you used TAC scaling or some other feature that actually allows you to eliminate some workload from the guest, in this case it would be a multiply and addition, then you could get a performance gain from using it on bare metal. But if you then go into nested VMX, you're not going to get a very good performance. So just remember that nesting is evil. And if you'd like to play with the code, I have pushed a working version into this GitHub. And I think we have a few minutes left, so I can go through the code. I would need to. What would I need to do to get rid of this? Oh, here it is. So currently it's a very simple implementation. The main init point is here in init kernel, right at the end, which is probably too late because we don't need that many kernel features, but still doable. And if you want to move it somewhere else. Yeah.
Zoom in.
Oh, zoom in? Okay. Sorry. Mm-hmm. Ooh, that might be too much.
That's good.
Okay. Good now? Yeah, sorry for that. But now I'll need to actually use search because... And then the actual code itself is in Arch x86 SV, and you just enable it in kconfig. It's under section self-virtualization. And don't do it if you value your hardware. The problem is that current VMX has some bug, and it doesn't work with it because it doesn't pass through interrupts. As the configuration that the self-virtualization using is quite rare and no guest has used it before, then the nested KVM that's implemented in Linux just didn't think of this. And sadly, it will take a while to get fixed as it's not really an important feature. So you have to run this on bare metal. And well, any bug you do requires you to reboot. So this is the main part, which takes care of the VMLAUNCH. You just load your state, and that's a big, long, ugly function that we might get to it. Write your guest entry, where guest entry is an instruction just after VMLAUNCH. Here, then take some stack into the host state and hypervisor entry into the host RIP. Then you just preserve your current stack pointer and launch it. After the launch, which is here, the execution is going to continue right here. So in case you missed something, you will get a VM entry error, and you'll continue just fine. And if it worked, you won't get any error, and it's going to continue right here, and the boot will resume at the point where you started to self-virtualize. If you get a VM exit, then it's going to go into hypervisor entry. It doesn't work. Hypervisor entry. which starts here and is just a block of code that saves the general purpose registers and then enters the VM exit handler that only reads the VM exit reason, and if it fails, it bugs. And the bug has a nice feature that on current Linux implementation, you just fall back out of the self-virtualizing into normal operation, so you can try again if this were a module. And if not, then you'll just handle the VM exit and VM resume, and this is going to continue all the way around. Probably the simplest VM exit handler is handle CPU ID, which, as you can see, is basically just read what the input to CPU ID would have been on the guest, execute the CPU ID yourself, and then load the output back. And I think I'm running out of time. So, still not perfect. Then we have there's some questions how to make all these VM controls into 0, because when you don't want any VM exits, you disable most VM controls you want, and there's quite a lot of them. And for example, if you wanted to have interrupts, you would just enable, or exceptions, you would disable, back. Exceptions, yeah. For example, right now we don't capture any exceptions because the exception bitmap is 0, but just switching it into a bit, which each bit represents one exception from 0, then you would get a VM exit for that. And similarly, you can trigger VM exits for almost anything you can imagine by configuring these VMCS controls. So that's all from me. I'd like to reiterate that virtualization is not the tool for every problem you might have. It can help getting you better for performance or isolation, but if you then want to virtualize back again, you lose all performance. And normal guests that are running under VMX usually trigger far more VM exits than what the self-virtualization do. So the overhead is higher. I would say 2,500 cycles for a minimal VM exit. So beware that any workload you run on bare metal might not run as well in a virtual machine. So thank you. And now, if you have any questions. Yes, please.
Do you plan to submit upstream?
Well, I guess I could do it. If I plan to submit it upstream, I guess I could do it on some April 1st next year. But the most upstreamable part of this is refactoring of VMX to make it reusable for, of KVM, sorry, to make it reusable for other projects. And then, well, finding bugs, which we already had, and fixing them in the emulation of VMX in KVM. But we'll see. Maybe if you want to make it upstreamable or build something on top of it, it's going to happen. other questions? Yes, then I guess we're done. So have a nice day and make it to lunch safely.
No, raz, dva, raz, dva, raz, dva. Vidíte blízko, jo? Jo, tak jo. Podržíte a čekáte, až to vypnu.
Right? Try to say something?
Test.
Yeah.